expanding space has significant implications for measuring distance. Consider a racetrack that's 100 kilometers long at the time the race car crosses the starting line, traveling 200 kilometers per hour. If we set its odometer to 0 when it leaves the starting line, it will read 100 kilometers when it reaches the finish line in half an hour. Now suppose the track is expanding at 50 kilometers per hour. How long will it take to reach the finish line, and how far will it have traveled? It will be more than a half hour and further than the 100 kilometers that the track started with. But it will be less than the length of the track when the car crosses the finish line, because some of the expansion will have happened to space the car had already traveled through. A little algebra gives us the exact numbers. Now suppose we didn't know the track's distance at the start, but we did know how fast the car travels, and the car's odometer tells us how far it traveled. And furthermore, suppose we found a way to figure out that space was expanding at 50 kilometers per hour. With that, we can figure the original track size, and we can figure out how far apart they were once the car reached the finish line. The principles are the same for light traveling to us from distant galaxies. Here we are zooming into GNZ11, the most distant object ever found. The galaxy's redshift, combined with Hubble's law, gives us the distance the light traveled, 13.4 billion light-years. And we know the speed of light, so the time traveled was 13.4 billion years. We normally say that the galaxy is therefore 13.4 billion light-years away. But during its long travel time, space expanded considerably. In fact, GNZ11 was less than 2.7 billion light-years away from us when the light started its journey, and the galaxy is now over 30 billion light-years away. In order to calculate these distances, we need to know how the universe expanded during the light's journey. It's not like the simple constant we used in the car racetrack example. In fact, we'll be spending the remainder of this video on just how and why our universe's expansion behaves the way it does, and we'll return to GNZ11 along the way. Note that if a galaxy is far enough away, its apparent velocity will be faster than the speed of light, and its light would never reach us. It would be beyond the physical visible horizon for the universe. It's not that it is moving through space that fast. It's just that more space is being created per second between us and them than light can traverse in 1 second. Plugging in the numbers, we find that all galaxies beyond 14 billion light-years could never be seen here. GNZ11 is now 32 billion light-years away, so the light that is leaving GNZ11 now will never reach us.